This is teacher Nicholus. Today we want to look at questions on surface area and volume of a frustum. And before we do that, first of all we need to familiarize ourselves with these solids. And number one is a cone. A cone is a solid like this. A cone is a solid like this. It has a circular base and a curved surface which narrows to a point that is called apex, this point here. So this is an example of a cone. The other one is pyramid. A pyramid is a solid like this. This is a pyramid. It has a polygonal base. Polygonal base which can be rectangle, square, triangle, hexagonal, and so on, and triangular faces like this, which meet at a point which is called vertex or apex, just as like in the case of a cone. The difference between pyramid and a cone, is that this one has a curved surface area, while this one, the surfaces here are triangular. They are triangular. That means they have edges like that. They have edges. So that is the difference between a pyramid and a cone. Another difference is that the base of this is polygonal. It can be a rectangle, triangle, or any other plane figure. But for this other one, the base is always circular. So that is, what about a frustum? If you have a cone like this, if this is your cone like that, you see that the base is circular, just as we said, and this curved surface narrows to form an apex. So if you cut it along this plane, which is parallel to the base, so that you remove or you chop off another cone, what you get is a frustum. So this is a frustum. So you can see that a frustum is like this. It has a flat top. A frustum has a flat top like that. So a frustum, just like a cone, has a circular. A cone frustum now has a circular base and also a circular top like that. And a fruster, there are two types of fruster. We have cone frustum and pyramid frustum. Cone frustum is the one that is made from a cone. When you cut a cone along a plane that is parallel to the base, you get a cone frustum. While pyramid frustum is a frustum that is made from a pyramid. For example, if you cut this pyramid, assume that these faces here are closed like that. If you cut it along this line here, what you will get a solid that looks like this. You get a solid that looks like that, whereby this here you also have another surface there which is rectangular or can be square, just like this other one. So this is what is called a frustum. So it's a solid which is a portion of or part of a cone or a pyramid that is normally formed when you cut off when you chop off a cone. A smaller cone from the original cone, or a smaller pyramid from the original pyramid. That is by cutting along a plane that is parallel to the base. So today we want to look at questions on surface area and volume of a frustum. So I believe you know how to get the how you get the surface area of a cone. If you look at my previous clips, there is a part whereby we looked at the surface area of a cone, and we say that surface area of a cone, surface area is a cone is gotten by surface area of a cone is equal to the area of the base, which is circular, which is pi r squared, plus the area of the curved surface. And we say that to get the area of the curved surface, we proved and found that it is pi r l. So that is how we get the surface area of a cone, whereby this is the area of the base and this is the curved surface area of the curved surface area of this part. So you add so that you get to the total area of surfaces. So if you have a cone, a frustum, that is from a cone, to get the surface area, of this solid, which is a frustum, it will be the area of this base, which is circular base, plus the area of the top circle surface, like that, plus the area of the curved surface. So it will be pi r squared, which is the area of the smaller circle, plus the area of the base, which is also circular, that is pi r squared. I'm using a different letter to represent the radius of the base because they are different. You can see this is a bigger circle, and this is smaller, plus the curved surface area, plus the curved surface area, or the curved surface area, this area here. So how do we get the curved surface area? So to get the curved surface area, the curved surface area, it will be the curved surface area of the bigger cone minus the curved surface area of the removed cone. The curved surface area. So to get the area, if this is your frustum, you can see that it has how many surfaces? 3 surfaces. That is this one, the top one, this other one, and also this, the curved surface. So to get the curved surface area, it means that you look, if this was your complete cone, it means that you look for the area of the curved surface area of the original cone minus the curved surface area of the removed cone, so that if you subtract, you are left with the curved surface area of the frustum. So that is how we do it. Therefore, this is pi RL, which is the curved surface area of the original cone, minus pi RL, which is the curved surface area of the removed cone. Remember, this L here represents the slanting edges, as we said before, these slanting edges. So that is what we mean by, that is what we denote with L, the length of the slanting edges. But because they are different, that's why I'm using capital letter to represent the original cone, and then now a small letter L to represent the slant edge of the smaller cone, removed cone. So that is how we do it. That means, so we can say that the curved surface area of a frustum is the area of the smaller circle plus the area of the bigger circle, which is the base, plus the area of the curved surface. To get the area of the curved surface, you look for the area of the curved surface of the bigger cone minus the area of curved surface of the smaller cone. That will give you the area of the curved surface of the frustum, and you add all of them, and that will give you the surface area of a frustum. For that was a cone frustum. For a pyramid frustum, you can see that the number of surfaces that we have there, we have this top rectangle, and we have this one base here, base rectangle, and we also have this these surfaces, which looks like, they look like a trapezium. They look like that. So this is one example of one surface there. So to get the curved surface, to get the total surface area of a frustum that is made from a pyramid, it means that you look for the area of this top, top, bottom, and also the side surface area. This one here you can get by saying length times width if it is a rectangle, and also this one you can say length times width, like that. But for this, you can see that it is what? A trapezium. It's a trapezium. So how do we get there? If this is your, because these and these are parallel, this is your A and this is B, and now you need to look forward for the height there. And now to get the area, area will be a half into bracket A plus B, which is the formula of getting the area of a trapezium. So it will be a half into bracket A plus B multiplied by height. And if you do that, then you multiply by the number of trapezia that you have. Like how many trapezia do we have? 1, 2, 3, 4. 4. So we could have multiplied by 4. So the surface area of that is how you do it. So that is how we get the surface area of frustum. You just look for the areas of different surfaces that frustum have. So there is a very important thing that we normally consider while looking for the area of frustum, and that is similarity. Similarity. So similarity is very, very important. So if this is your original cone, this is your, and you are cutting it along this line here, you will form a smaller cone there and a frustum. Yeah. So if this is your original cone, this is removed cone, and this is what? Frustum. That is frustum. This is what I'm saying. This is your original cone, and if you cut it along this edge, you will have this smaller cone, which is this, and a frustum. Yeah. So there is something that is very important that I want us to learn. So there are some dimensions that will help us to calculate the volume or the surface area of a frustum, and that is, you see this circle is different from this. Their radii are different. This is a bigger radius and this is smaller radius. And also we know that this arc length here, which we can replace with L, and this one here, we can denote it with L, smaller L, like that. So this triangle, this cone here, the original cone is similar to this smaller cone, removed cone. How do we know that? If, for example, you draw perpendicular height to meet at the center so that you have a right angle triangle like that, and then again you draw another one here. If you are considering these cones, this cone here and this one, you can see that because this is just part of this angle here, this angle here is the same as this, which is shared by the original cone, which is the bigger cone, and a smaller cone. Another thing is that this one here is a right angle triangle, likewise to this right angle triangle, and this angle here. To get this angle, it means you will say 180 minus this angle plus, 180 minus the sum of this angle and this. So that means this angle here, if this is alpha, this one also will be alpha. That means all the triangles are equal. The corresponding triangles, the corresponding angles are equal. And if the corresponding angles are equal, then we can conclude that this solid here and this one are similar. And if they are similar, then it means that for similar figures, similar figures, for similar figures or figures, the ratio of their corresponding sides or lengths is constant. Yeah, so having said that this solid here, the original solid cone and this one are similar, it means that the ratio of their corresponding sides is constant, is always constant. So that means the radius, this radius here, radius of the bigger cone divided by the radius of the smaller cone, which is still this one here, divided by the radius of the smaller cone is equal to the perpendicular height. This here is a perpendicular height of the original cone or the whole cone divided by the height of the smaller cone. That will give you the same figure as if you divide the length, slanting edge or slanting length of the bigger cone divided by the slanting edge length of the slanting edge of the smaller cone. So all of them will give us the same value. All of them will give us the same value. So that is very important. That's one thing that we need to understand, because it will help us to calculate the unknown dimensions later when we are looking when we will be solving questions to do with Frustum. So that is what is very important, and this is what normally students fail to understand. So remember that it is this cone here which is similar to this. The original cone is similar to that. And radius, bigger radius divided by smaller radius equal to bigger height divided by smaller height, which is equal to bigger slanting length divided by smaller slanting length, or the slanting length of the smaller cone. And if you decided to start with the bigger radius, it means that when you are looking for the ratio here, it means that you also do the same for the height and likewise to the length. Yeah, you cannot mix. You cannot start with smaller here. To take it as a dividend, and you take capital H to be your dividend on the other side. If you have decided to start with the dimension of the bigger cone, you do the same for the other dimensions, so that you get the accurate or the correct figure. So that is one thing that we need to understand. Another very important thing that you need to understand is that if you are given a Frustum like this and you want to use it to complete the cone, what you need to do is that you need to identify where the side where the apex is. So if we join this Frustum with a cone like that, so that we have a complete cone, this is our apex or the vertex of the cone, so that this line here you will extend it to meet with another one here, so that they form what? Apex. That is to say that the apex is always on the side of the smaller circle. That is for you to remember. You should know that the apex is always on the side of the smaller part, the smaller circle, like that. So if, for example, a cone is drawn for you like this, and you need to complete it, so that to get the original cone, what you need to do, you just extend this line, and also you can see the side where the line will tend to meet. So they are most likely to meet on this side than this side, because if you extend on this side, it means that will go that way, and also this one. So they will meet at a point there. But if you extend on this side, they will never meet. So always know that the apex is on the side of the smaller circle. Also, you can be given in this way. So where do we get our apex? The apex will be it cannot be like this, but this is the smaller circle. This is a smaller circle, meaning that the apex will be on this side. So if you join them like that, this is our apex. So it is also important that you understand this. Another thing that we need to know is that normally you are given examples of what is available or what you normally use. For example, I have a glass here. And this is an example of a frustum. It's an example of a frustum because you can see that it was supposed to be a cone, whereby if you join it like this, the apex was supposed to be on this side, but now it has a flat top and also bottom. So this is an example of a frustum. Another example is maybe a lampshade or a pail or a bucket. So those are some of the examples that examples of a frustum. So it's good that you know, so that when you are solving the question, you know what you're supposed to do. Like now, if it's a glass, you know that this side here is open. So the surfaces are the bottom and the curved surface. So this one here is open. Yeah, so if you are looking for the surface area, you need to calculate the area of two surfaces. This one and the curved surface. Yeah. And if it is a lampshade, mostly it is open-ended, both sides. So you need to calculate the curved surface area of the curved surface area only as the surface area of that solid. If it is a bucket, we know that unless you are told it is closed, mostly it is open also. You calculate the area of the base and the curved surface area. So that is what I wanted us to understand before we embark on the questions. So now I want us to do some questions so that you see how we can apply what we have just learned in solving the questions.